Okay, welcome everyone to the Saturday issue of the Software-Defined Storage Dev Room. Thanks for coming. If you want to see more of that next year, give some feedback, then we maybe even get 2 full days. And in the meantime, give it up for Ricardo for the first talk.
Thank you, everyone. So today I'm going to talk about the work we have been doing on the Ceph project, about rewriting the wire protocol that is used in that project. This is an outline of what I'm going to share to you. We will start just to give an introduction about what is the Ceph messenger, and then we will briefly talk about the messenger API and show what are the current wire protocol limitations and why did we decide to implement a new one or design a new one. And then I will give some more details about the design and the implementation of the new wire protocol. All right, let's get started with what is the Ceph messenger, basically. So it's a wire protocol specification, but it's also the corresponding software implementation of that protocol. So when we talk about Ceph messenger, we are talking about implementation and the protocol specification. Normally, users don't hear about this. It's invisible to users, right? And if users hear about this, it's because something's not working properly. Okay, and we don't want users to hear about the Ceph messenger. Another important thing is that Ceph messenger does not know anything about what happens with with the other Ceph components. So the Ceph messenger doesn't implement the algorithms used for other components that perform, like the operations in OSDs, mons. Ceph messenger is just the communication library used for these components to talk between each other. So where can we find it in Ceph? Well, basically we can find it everywhere. So every component, every daemon has this small code that is used to communicate between each other, and also the libraries, the client libraries also have this code too, so that they are able to talk with other components. Right. So, as I said before, the messenger is the small communication library that is used for the components to talk to each other. It can be used both as a server or as a client. It's the same code for both, and this communication library abstracts the components that use them, abstracts the transport protocol that is used. So this runs on top of POSIX sockets, RDMA, or DPDK. And it gives you, it's going to use a reliable delivery of messages, and it also gives you an exactly one semantics. And besides that, it also it also abstracts part of some temporary connection failures. So when there are failures at the transport level, it takes care of reconnecting to the peers and making them more transparent as possible for the applications that use them. Okay, so the API is very extensive, but we can focus only on what's the important. So the programming model for the applications that use this small library, they basically they connect to another peer by giving an address, and you receive the connection. So very simple. And then you can use this connection to send a message, basically. And you can also tear down the connection. You can also register a dispatcher where you can implement some callbacks that will give you that you need to receive message. So you implement a callback that is called when you receive a message, so which we call dispatch. And you can also have a callback when you receive the new connection from another peer. Okay? So this is a high-level abstraction over a communication channel. Okay. So you also in the API you also take care of, you have callbacks for taking care of the authentication between the peers. So until now Ceph has a wire protocol since the beginning, right? The components need to talk to each other, and the current protocol is still the first one that was developed since the beginning, so it has a few years now. And one of the problems was it's not easy to extensible to add additional states to the protocol, at least in an early stage. So it's very hard. It has in the beginning there's no flexibility to change. It doesn't provide data authenticity, so the payload of the data that is sent through using this protocol is not possible to guarantee its authenticity. There's also no encryption supported, and it's also limited in the support for different authentication schemes. And to finish, it also doesn't have a strict structure on its own internal messages of the protocol. So it's a bit ad hoc in the way that well, it has evolved. It's the result of an evolution of many years of patches, and yeah, you know how these things work. So. So it was time. So these limitations, we were not satisfied, and we wanted to design something from scratch that could fix these limitations. And so we started the design of the V2 protocol. Okay? And so this new protocol, it's a completely different protocol. Will be available in a different port, and we will still keep the V1 protocol. So when we add this new protocol, components will basically talk both protocols in different ports. This new protocol is being developed for the next Ceph release called Nautilus, and only the user space libraries will talk this new protocol. For instance, the kernel modules will still talk V1. Okay. And as I said, so Nautilus has not been released yet, so this is currently under development, and we hope that we can finish it on time. So the protocol is a complete redesign and implementation. It's designed since the beginning to be extensible in the way that we can change the protocol behavior right from the beginning, well, almost right from the beginning. And we didn't want to impose any limitations on the authentication schemes that we want to use with this protocol. And we wanted to fully support encryption on wire. So what I'm going to show you is now it's a very high level idea of how this protocol, this new protocol works. So as a start, we will have two actors, the connector and the acceptor, okay? Where the connector is always the entity that starts the connection, and the acceptor is the one that is accepting the connection. And the protocol has four phases. It has the banner exchange, which is the first one. Then the second phase is where the authentication between the peers is performed. And the third is after the authentication, the protocol establishes a session between the peers. And then as soon as we have a session between peers, both peers can start exchanging messages. So one important, and sorry about specifying this with code, but it was so much easier. One of the units of data of this new protocol is that all internal messages of the protocol are exchanged inside these structures that we call frames. And the frame is actually a very simple thing. It has a length, it has a type, so there are many kinds of frames, and then you have a payload, okay? And all the things we send between each other peers are enclosed in frames. And the same thing for when we start to encrypt the payload, we will basically have an encrypted frame, which it resembles, it's still a frame, right? It has a length, a type, and only the payload is encrypted. Okay, so the first phase in the banner exchange, the peers, both, as soon as the transport layer establishes a connection, for instance, with sockets, you have a TCP. As soon as the TCP connection is established and the acceptor has received it, they both concurrently send a banner to each other. And the banner includes, besides the string saying Ceph v2, it includes two very important things, two feature masks that are called the supported features and the required features. And with this information of what are the features that each other's support and require, we can decide what to do from that point onwards. Okay, so as soon as the banner exchange finish, we can actually, our protocol can change. Okay, so in the future, if you have new features on the protocol, we can change the state machine from here in. Okay. So after the banner exchange, they also exchange the information about what kind of entity they are. So if they are OSDs or MONs or clients or MDS or the manager, and they also tell each other what is the address of the peer. Okay. I will not go into details why we need this information, but that's how it works right now. So after this, we go to the second step, the authentication. And the authentication is started by the connector. So the connector says to the acceptor, I want to authenticate, and I want to authenticate with this method. And this method can be none, so I don't want to perform any authentication. Okay? Or it can be using CephX, which is what it's the system we use for authenticating the Ceph components, or can be any other method that we add in the future, like Kerberos or something else. We also specify at this point what do we want, what guarantees of security we want after the authentication, regarding, for instance, if we want the payload to be encrypted or just signed, or we just want some integrity checks using CRCs. Okay. So the connector sends this message to the acceptor, and the acceptor looks at what the connector wants, and it might reject. So if, for instance, if the connector wants no authentication, the acceptor can say, I don't support that, and gives the connector what are the methods that I support. Okay. and the connector has the possibility to send again an auth request message to the acceptor. And as soon as the acceptor receives and accepts the auth request, it can ask more information from the connector, depends on the authentication scheme that is being on. And this new information that the acceptor sends to the connector, asks the connector can also replies to the acceptor, and the acceptor can again ask for more information. So we can have several round trips at this point if the authentication scheme requires it. Okay, and this was one of the limitations that we had in the V1 protocol, which only one round trip were. Well, no, it was not easy to extend to have more round trips. So the last messages, the entity that finishes this is the acceptor by sending an auth done message to the connector saying, okay, the authentication is done, and we can proceed. Okay. And from this point, if we have chosen that we want our frame payloads to be encrypted, then everything from here, session establishment and message exchange, is encrypted. So session handshake, it's actually really simple. So the connector sends some information that identifies itself, and the acceptor looks at it, and if everything is okay, it just replies saying it gives its own information. And there's also the other case, which is when some peer is actually reconnecting. So imagine a case where there was a failure while the peers were communicating, and the client the connector can actually reconnect to the acceptor. And at this stage, instead of sending the whole information, he just sends, oh, I want to reconnect to a previously existing session. Okay? And the acceptor will have the job to see, okay, yes, I know this session, so I'm going to reconnect you to this existing session, and you will continue onwards. Okay. So very, very simple, very explicit protocol. So after the session is established, we go to the message exchange, and at this point, actually, there's no more a connector and an acceptor. Both are peers. Both can send messages concurrently in any order, and then the protocol also handles the hex of the messages, the acknowledgements. So they send messages. The acceptor can piggyback acknowledgements in other messages, and if the peer is not sending any message, we have a special acknowledgement message to say I already received up to that point. Okay. So this is the high-level overview of how this new protocol works. So in this protocol, we need to guarantee, we give the guarantee we can give integrity, authenticity, and confidentiality on the messages using the new one-wire encryption feature. And integrity is given by CRCs in the frame header, and also CRCs in the message payload. Authenticity and confidentiality are given. You only get this for the payload of a frame, so tags, the kinds of the frame length and the frame tag are not signed or encrypted. And authenticity is given by message authenticated codes using SHA-256, at least for now. But actually, this protocol, we can we can specify multiple authenticity schemes and protocols, or even multiple encryption modes. Okay. And confidentiality currently is given by AES encryption. So the source code, if someone wants to look at it, it's currently, so you have to clone the project, and you have in this file, it's the implementation of the whole protocol. You also have a file called protocol v1 where you can see the v1 protocol, and you can also see, oh, it's cut, but you can have also read the specification draft of this protocol in the Ceph docs page. So, future features for this. Well, we would like to add more kinds of authentication protocols supported, especially Kerberos. One thing that we have been talking but still don't have plans for it is the connection multiplexing. So if you want to collocate, for instance, many OSDs in the same process, we want to avoid having actually many physical connections per each OSD for the other peers, and we want to reuse the same connection to the other side. So for that we need to multiplex it. And well, this is an extensible protocol, so new ideas and contributions are welcome, basically. And yeah, we're done.
Any questions? Got plenty of time.
Yes.
What types of AES encryption are supported? For example, only CBC or other types as well?
Yeah. So the question was, what types of AES encryption do we currently support? That's a good question, because I don't clearly remember what we are currently using. Maybe CBC? CBC? No?
The initial implementation used CBC, but
Yeah.
current draft, that's probably going to be a no, which is the AES CPN.
Yeah.
So it combines the encryption and the signature of that, and it's faster than TCP.
And does it support hardware acceleration as well?
That is the plan. So we're trying to structure the code that will be filtering off it. I think we're using OpenSSL.
Oh, that will be fine.
So I'm just going to repeat briefly what Sage said. So yeah, we initially were supporting CBC, but now we're changing it to AES GCM, which takes care of signing and encryption, right? So that's yes.
Just one question about, so I didn't know about Ceph using other message brokers centralized like RabbitIQ. And just a question about if I have an application and I use the Ceph library, do you have some kind of thread which is continually pulling, or I don't know how it works in this direction? Do you allocate once per session and you wait? Or allocate and continuously, what is the mechanism inside?
So, so the question was, how does the Ceph messenger actually is currently working? It's like
Exactly. So the big difference is because in RabbitIQ
you have a central.
more kind of a blocking connection. So you take the socket and you open it, and you continue as the socket open and send messages and making a pull to receive the new.
Right, right.
And
So-
what about Ceph?
so in this here, what you do, we use non-blocking sockets, non-blocking connections, and we rely on the operating system event system to be notified when we are allowed to read, when there's something to read on the sockets, or when we can actually write. So it's, and so every daemon that when it instantiates the messenger, it instantiates this mechanism. It creates if it's bind, it creates a socket for accepting connections, and it changes to non-blocking mode, asks the operating system to start to receive notifications for that connection, and that's how it works.
Do you think with this new feature set that the communication is hardened enough to use such communication over a public network? Because normally the advice is to do it on the open private networks.
Right. Well, oh yeah. Sorry. So the question was if with this new protocol, the Ceph messenger is now a good fit to be used in a public network for the components to communicate in a public network. I really don't know what to answer to that question, because I don't know what are the threats that
That was not the target.
Right, that was not the target, okay? Yeah. And yeah, I don't know if I would, I don't know, okay? I don't have enough knowledge to answer that question from this point of view. Yes?
So why add the overhead of encryption if you can't use it over a public network?
Well, that's, so the question is, why adding the overhead of encryption if we cannot use the Ceph messenger on the public network? Well, you might have some requirements, security requirements, that all data that is, so imagine you're storing user data in the data center, and you have some requirement that the data must be always confidential, because you might have some very curious sysadmin that starts starting sniffing packets in the network. So inside people, and you have the requirement that you must guarantee that users' data is actually, it's confidential and no one can actually see. So the only way to achieve this is if you actually encrypt all data, even in a private network.
Ricardo, in that sense, is it possible to specify in some config that, let's say I have an east and west part of my cluster, and there's public network in between. I would like to have security on the large link and internal in the local network. I would say, well, okay, I don't care.
Mm-hmm.
Can I specify per link whether I need it encrypted, or is that just an overall decision in global config?
So the question is if the messenger can be configured to configure it in a way that we can specify if we want a secure connection only for some links, right?
Between all these
That's essentially a stretch.
Sorry?
That's essentially a stretch cluster.
Yes, but
You're
I see that coming by on the dev list and on the users list that people are creating east and west
Right.
type clusters.
But you are sharing the same public network.
The problem is how do you characterize a link? That's where I'm struggling.
Yeah.
In this case, it's literally the physical link.
The protocol allows you to negotiate the connection modes you allow or require on a per.
Yes, okay, but is there
The
any
configuration right now is per type.
Right,
so
yeah.
the whole cluster is either encrypted or not encrypted?
There are like 4 or 5 settings. It's like there's a setting for internal to the monitor has one node, connecting to the monitors has one node, internal to all the daemons, exclusive of the monitors OSPF addresses, and then client connected to this cluster. So within those buckets, you can control what's
Oh, that's
required.
the MS bind, OSD, V2.
But they're new settings
Yeah.
for whether
Yeah, that's the one you mailed me.
Yeah.
Yeah. So overall, the thing is that currently we can only distinguish between type of peers to change the configuration. So you can say that between your OSDs you have this configuration, but it's with the type. It's not individual instance of daemons. Which one? I don't know. Okay.
I don't know.
Please go ahead.
Just from my point of view, what would make sense to me to split the encryption and have non-encryption connection is if you can configure it in a way that you have, when you have a cluster network and your client network, that you have, for example, the encryption on your client network links, so that everything that accesses the RVD block storage, for example, it gets encrypted, but not the replication in between the clusters.
Yep.
So from this point of view, that would make change the sense to have this option.
Yes, and that you can do, because you can say, so every client is required to it only works if we encrypt if it accepts to encrypt the messages, and for other types you say no, I also allow to not to do that. So hello.
You've got some types in your message that aren't encrypted. What was the rationale for not encrypting the types, and how much could you infer from the types of messages and the order of messages?
So the question is, why didn't we decide to also encrypt the frames tags in the protocol? It's a good question, because why didn't we do it? Oh, okay. All right. So Sage is saying, because I was not present when the protocol was designed, but at the time we were thinking of implementing the connection multiplexing, which I talk about in the future features. That was supposed to be implemented with the new protocol, and at that point we needed to. There was no way to. If we encrypted that information, we probably wouldn't be able to distinguish some messages. So.
Because you would have, the idea with multiplexing is you would have some number of OSPs on two communicating processes that are sending messages to each other, but each OSP has its own independent secret key and negotiates a different encryption key with each other peer OSPs, and so you have these concurrent streams.
Yeah.
So we had to have a shared channel.
They need to know from whom comes the right. Unless you do encryption on top of encryption, but that way you are actually doing a SSH tunnel. So yes.
So you mentioned plans to add Kerberos authentication. So can you give some guidelines on how to choose the authentication method in the future? If you compare Ceph and Kerberos, so which one?
So the
If one has the choice.
So the question is, if we have in the future, when we have support for more authentication protocols like Kerberos, if we have some guidelines to help the admin to choose which one to use. I'm sorry, but I'm not that I don't know so much about these security protocols to answer at this moment that question. Well, actually, Ceph was based in Kerberos, so I don't think there's too much of a difference between choosing the current Ceph and Kerberos. It's just a matter of if you already have the infrastructure, everything use Kerberos, and then you can actually leverage it in the Ceph instead of having one more security protocol to manage keys and manage access. So the rationale for having Kerberos as a next step is because if you have that infrastructure already, it will ease you a lot, right? Because you already have the infrastructure to manage it. Okay. So.
Thanks, Ricardo.
Thank you.